Today we will start on and we will look at sectional forces in beams. We are still in the statics realm of mechanics, that means things are not moving, where everything is at a fixed this thing. In the last class we saw how to look at problem of trusses, and we now often when we encounter structures we encounter what we term as beams. Beams are thin prismatic members which are loaded transversely and oblique or axially. And what this means is that we would have a thin member. So, AB is what I am referring to as a beam, it is a thin member AB. It is a prismatic member. What do we mean by prismatic? That its area of cross section, it may have any shape, it could be circular, it could be rectangular. It runs the same across the whole section. And now what we talk of is that if we have a beam like this, on the beam there could be a loading. So, this is what we term as a distributed load on the beam, and this is a distributed transverse load, a load perpendicular to the centroidal axis of the beam. So, this is what we mean by an axial load, it is a distributed load. In addition to this, maybe we also have a plane load, a point load, this is again a transverse load. In addition to this, there could be an axial load, a force along the centroidal direction of the beam is what we term as an axial load. Now, here what we would like to know is that if we have a beam like this which is loaded, and if a section XX is cut somewhere on the beam. So, we take a section XX which is cut on the beam. So, now what we would like to know is on the cut section what are the forces and moments, and these are what we refer to as the sectional forces in beams. So, we cut a section of the beam, at the cut section we would like to know what are the forces and the moments which are coming there. Now, we have a terminology for this, and so let us see, suppose we have a section like this and this is where we have cut the section, this is the section XX. Now, we have an axial direction which is basically the centroidal axis. Let us call this direction as En. Okay. Now, perpendicular to En, we will have two more directions. We will have a direction here and we have this. So, En is the axial direction, and perpendicular to En for a general 3D case, we will have two directions which we term as Et1 and Et2. Now, I come to the nomenclature. So, is that clear? I have a straight member, I cut the member, the direction along the axis, a unit vector along that, I call that as En, and perpendicular to En, there will be two more directions, I call them as Et1 and Et2. Is this clear? Now, when I look at a general loading of the beam, and when I cut a section, at this section, what do I get? In general, when I cut a section, I will get a force and a couple, or a force and a moment, which would be in any direction. So, when I cut this section, at the cut section, I will get at cut section, there will be a force and a moment in any direction. So, this could be depending on the loading, it could be in some arbitrary direction. For specific cases, you may have some simplifications, and we will look at the planar case, where in planar case we will find there will be only Et2 and En, and the couple will be only about the z axis, which is about Et1. But in general, we will have this. Now, what we do is we define. So, now this is where now the definitions come. The sectional force or the internal force along the En direction, this is referred to as the axial force. So, we have a name given to the force along the En direction, it is called the axial force. And the sectional force along Et1 and Et2 direction, this is what is referred to as the shear force. So, that is the name given to these forces. Force along the axis direction is the axial force. The two components along the two perpendicular directions are termed as the shear force. Okay. So, now for example, if at the cut section the force is vector F, then the axial force is equal to F dotted with En, and if I want to make it as a vector, I will put En also. So, this is the axial force, and the shear force has two components. Along Et1 and Et2, and we write the shear force is equal to, so I write the axial force, let me put it along with the direction. So, the shear force will be nothing but the total force F minus F dotted with En along En, and this will be equal to, I could write it as Ft1 Et1 plus Ft2 Et2. So, it will have two components of shear, along the two directions. Is that clear? So, that is the name, that is the meaning of shear force. And so, if you know a general force F which is there at the cut section, you take its dot product with E and you get the axial force, you take its components along the other two directions, you get the shear force. And if you can't find it, basically you can use this general formula. Okay. Now, similar to this, if we look at the moment, then the component of the moment at the cut section along En, this is called, or this is what we define as the twisting moment. If I have a bar like this, a moment which is along this axis, what does it tend to do? It tends to twist the bar. Twist is actually, I do not know, these days twist is quite unpopular otherwise, or not very popular in vogue, but otherwise there was a dance form which was called twist. And where, what did the, how did this dance form twist work? Basically, the body was twisted about its axis. That is how people used to twist. At least I don't know about, I don't know too many English films, but there was a very old Hindi film called Gumnam. And if you have, there is one song there, Jaan Pehchano, where the people are twisting their bodies about their axis. Maybe next time I will get a clip of that twist and show it to you. So, that is what, so twisting means basically you rotate about the axis. Now, the component of the moment at the cut section along ET1 and ET2, this is referred to as the bending moment, because this moment, this tends to bend the beam. We have a beam on which I have a moment which is about, if this is the beam, moment is about that axis, that means you are trying to turn about that axis, it will tend to bend. Or if it is about this axis, again the role of that will be to try and bend the beam. So, now this is how we define axial force, shear force, bending moment, like this. Now, if we look at a two-dimensional planar loading, which will be the focus in this course, we will, if I look at two-dimensional planar loading, then I will have a case like this. I have, let us say this is the x axis, this is the y axis, the beam is along, there is a beam AB which is along the x axis, it has some support like this, it is loaded like this, let us say there is a force F acting like this. So, in this case, when I cut a section XX, I will look at the section AX, and then what I will find is that at this point, this will be the axial force, a force here will be the shear force, and we will find that there will be, because of this loading, you will only get one component of the moment which we call the bending moment. So, this bending moment would be about the z axis, the axial force will be force along x, and the shear force will be force along y. So, in a planar loading we will have an axial force, one component of shear force and one component of bending. Okay. Now, it turns out the bending moment is an important quantity, because if I look at a beam and if there is a moment which is bending it, then what it tends to do to the beam is it tends to deform. And if I look at a surface at the top, it will tend to get extended because of the bending moment. It will, if the surface was initially like this, and if it is a load is acting like this, it tends to curve the beam. So, it tends to elongate the beam, and therefore, stresses are caused in the beam because of bending. And what becomes very critical is the point where the bending moment is maximum, because the stresses are directly related to the bending moment. So, the beam should be designed in such a way that it should be able to take that stress. If it is not able to take that stress, it may fail, it may break, and that could lead to a catastrophe. So, that is why calculating bending moments and shear forces become important, because they are related to the stresses which arise in a beam. Now, luckily for us in this course, luckily or unluckily, we will not look at the stresses, we leave that to the solid mechanics course. What we will see in this course is, what you should be able to do is, given the loading on a beam, you should be able to say at a section XX what are the shear forces, what are the bending moments. And leading from this is the concept of what we call a shear force diagram and a bending moment diagram. If I plot the shear force as a function of x along the length of the beam, then this plot is what is called as a shear force diagram. And similarly, if I plot the bending moment as a function of x along the length of the beam, then this diagram is called the bending moment diagram. So, therefore, what is important is we have to then look at the, from shear force we come to the shear force diagram and the bending moment diagram. These are plots of shear force and bending moment as a function of length along the beam. And these will become clear once we talk a bit more about these. I will just explain this. Now, instead of specifying the shear forces as positive or negative, or saying it is plus y or minus y, we have a sign convention. And the sort of slightly ambiguous part of this sign convention is that for the shear force, there are two types of conventions which are followed. So, we will follow the convention which is followed in the textbook, and which is generally followed by civil engineers, not by mechanical engineers. And in this convention, what we have is, if we are plotting like this, this is the x direction, this is the y direction. If I look at the positive, if I look at this face, the outward normal here is along plus x axis. Now, the shear force as per the convention of the book on this face, we write the shear force as V, and what we have is a down on the face where the normal is along the positive x axis, the downward V is taken to be positive. So, we will call it as shear force V if the cut section, on this cut section, if the force turns out to be pointing downwards, then that is what is referred to as positive V. If the force, you calculate the force, it turns out to be in the plus y direction, you will call it as minus. You will, if suppose the force in the vertical direction is plus 10 newtons, so it will be called as V is equal to minus 10 newtons. So, this is how we have the sign convention, that a force like this is what we call as the positive shear force is like this. Now, the how the sign convention work is, suppose if I look at, if we look at the right section of the beam, the right section of the beam, the same face will come, but from the other side. We have cut a section here, on the top I was looking at the left section. Now, in the right section if I look at it, the outward normal is in minus x direction. So, here the convention which we take is, on this face V will be shown, if it is in the upward direction on this face it will be termed as positive. And the reason for this is because when you now combine the two, they will give you a net of 0. So, therefore, when we talk of a sign, when we talk of a shear force, it is positive or negative, it will not depend on whether you are taking the left section or the right section. So, on a section which is like this, where the outward normal is in the minus x direction, upward force is considered as positive V and a downward force is considered as negative V. Okay? So, this is for the shear force. What about the moment? For the bending moment, we have an unambiguous convention, and that is what is used in all textbooks. And what we find is a counterclockwise moment on a positive face is considered, is treated as positive. So, if on the cut section the moment turns out to be counterclockwise, counterclockwise means x cross y, and you see the direction will be plus z. So, a counterclockwise moment is treated as positive. If the cut section, the moment on a positive face, what do I mean by a positive face? Whose direction of the outward normal is along positive x axis. That is the meaning of positive face. So, a moment which is along plus z axis on a positive face is treated as positive. So, now on this face, what will be treated as a positive moment? This is a negative face, so a clockwise moment. So, on this face, if I have to put the moment as positive, that will be clockwise moment. So, this m, a clockwise moment treated as positive on a negative face. A negative face means outward normal along minus x axis. Okay. So, this is just, these are the names and the definitions. After that, actually it is nothing but simple statics. Counterclockwise viewed from the front, x cross y. So, basically if you are looking at it, it is a right handed coordinate system, x, y, z. So, counterclockwise means z positive if you are looking at a right handed system. No, so you are looking at it from the plus z side. X cross y will always give you z. You go with right handed coordinate system, go from x to y. I think it is very unambiguous. No, so if you flip y, then it is not a right handed system. If you, or then z will be going inside. See, you will be able to flip, if you flip both the things, then what is the issue? If you flip y,
then the x is the same and z has changed. So
no, then y also will change. Na? You can't have only one change. If it's if the system is still to behave right handed, two of them have to change, not one. So, maybe we can discuss it. I don't. See, okay, the convention is, let's look at x, y, z are unambiguously defined.
No, sir. The object is defined.
No, on the object, you choose x axis as the positive x axis, y axis. If you choose y like this, then z has to be outside because it's a right-handed coordinate system. So now in this system, if we have things like this, now here a positive shear force will be the one which is downwards. That is how we have defined V. Some books will define, as I told you, on this face they will define it as upwards. But we will follow the textbook, so we will call it downwards. Now the moment which is on this cut section, which is along the plus z direction, is treated as positive. Now if I look at a section like this, obviously if V and M are like this, on this section V will be opposite, M will be opposite, because they are the same section. Now on this section, this V which is pointing upwards, this is what I call this as a negative face. A negative face means the outward axis is in the negative x direction, whatever you have chosen. So there a positive V, a positive shear force will be positive, and a clockwise moment which is actually along minus z direction will be treated as positive. So basically you have to look at the face. Positive face, positive moment is positive. Negative face, negative moment is again positive.
So, sir, if we flip the body along the y-axis,
Flip the body means if the body is there, the loading is there. What do you can flip the axis, you are not flipping the body.
we rotate the body.
No, the road, once you rotate, you have body is fixed with a given configuration. It is the axis which you can flip. I don't understand, if you are flipping the body, then it's a different configuration. Then you have to make axis according to that. So if you flip, if you have a beam like this, now in a physical beam you can change the axis. I don't see what do you mean by flipping the body. And if you flip the body, then you choose your x and y along that and follow the same convention. Maybe still if there are doubts we could discuss. I don't want to discourage your doubt, but think about it and then we can talk about it. See, normally it is the axis which is to be flipped or which is in our hand, not the body. Body is at there is a given body at a given location, given orientation with some loading. What I can do is I can choose, as you said, maybe I choose my y downwards, y upwards and so on. So those are things which I can. Okay. So now given this, how do we actually find the shear force and bending moments? So a typical problem which we will have, let's have a look at let's first see what a typical problem could be. We have a beam AB. I seem to be, now there could be different loadings. There is a fixed axis, a roller. I am trying to draw beams which are statically determinate. Okay. So it could be a cantilever end at one end and hanging like that. All these you will come across, and there is some general loading. Let us say we have a force Fx, we have a moment acting at this point, and there is a distributed load, and we want to find the shear force and bending moment at different sections of the beam. Or I could be asked to find out draw the shear force and bending moment diagram of the beam. Okay. So now when we have to do this, what we will do is we will first thing we will do in a problem like this would be to find the reactions. This is done in almost all statics problem. We will start with finding the reactions. Then we move from one end. Now, I am assuming the problem says draw the shear force diagram. If the problem says, if the problem is of this type, that you have to find the shear force and bending moment at the section XX. How would you do it? Then what you will do is, you draw a free body diagram of either the left side or the right side of the beam, one part of the section, and then you expose the shear forces and bending moment, and then you write the equations of equilibrium. Sigma fx is equal to 0, sigma fy is equal to 0, sum of moments is equal to 0, and that would give you the shear force and bending moment. But now you will have to keep the sign convention in mind. Suppose if you are cutting a section from the right side, then you will show the shear force, unknown force, positive as V, and a clockwise moment as M, and then if your answer is minus, the answer will be minus. So that is how you find shear force and bending moment at a section. All you have to do is just, so if I have this, then I will draw the section Bx of the beam. I have already worked out the reaction By. Now on this part I have a part of the trapezium loading. The full loading goes on from here, but I have cut a section at X. So therefore I will include only that part which is there in my this thing. So I will keep only this part of the loading here, and then I will show here at this section I will show an unknown force V and a moment M, and then what I will do is sigma fx is equal to 0, this will not be needed here, sigma fy is equal to 0, and sum of moments about any one point. I can take them about x or sum of moments about b is equal to 0. I need to do it only about one of these, and this will give me the value of v and the value of m. I will get these two values by performing a static analysis. Force balance and moment balance will give me the values of v and m. Is that clear? So this is how one finds the shear force and bending moment. Now such a process could be tedious, and it turns out we have some simple rules with which we can work out the shear forces and bending moments in a rather easy way, without at times even drawing the full diagrams like this. So this is the general mechanics principle which is there. Okay, I could alternatively have drawn the free body diagram of the left side of the beam. I could have also taken the left side, then I would have taken the force here on this side at A. I would have shown Ax and Ay, I would have shown this moment, and I would have shown this part of the distributed force. But now what I would have done is I would have shown V as downwards and moments as counterclockwise, and that is what once I would have solved this. So that means if I take, if we take the left section, then we would have Ax. At A I would have got Ay, Ax, I would have got this force, I would have got this moment which is there, and I would have got the starting of the trapezium loading at the section X. But now the key would be, I would have shown V like this, and I would have shown moment like this, and once again if I do sigma fx is equal to 0, sigma fy is equal to 0, sum of moments is equal to 0, I will get V and M. And because the beam is balanced, whether I use the right section or the left section, I will get the same answers. And the sign convention ensures, because we have taken V and M and defined them in opposite directions, there will be no confusion. Hopefully this should clear your doubt. It does, okay, thanks. So now, once we have this, now are there some simple rules? Because this sort of an approach is quite good if we have to find at any one section. If I have to draw a shear force and bending moment diagram of this beam, then what do I do? Is there a straightforward way by which I can draw the shear force and bending moment diagram? So now let us look at that. Is there any doubt or any questions? So we have some simple rules, and what we have is, so let me move to the next page. Suppose I am talking of a beam, let us say there is a force P. So if I try to see, I use a symbol zeta for the distance between the cut section and the force P. So now I am starting from the left, I am starting along the positive x axis. I have a force P. What I try to see is, what is the role of P on V? What will P do? If this has to be balanced, then what I get is P plus V must be equal to 0. So therefore V must be equal to minus P. So a downward force of P, I can think of it as a downward force of P induces on all sections to its right a shear force equal to minus P. Okay. So I can think of it like this. So therefore what force balance tells me is, I get my rule number 1. So this is just talking about P. Reaction at A, I will come to it. So a downward force P induces on all sections to its right a shear force V is equal to minus P. Okay. So this is the role of P. Now this is what P does. Suppose if there are 4 forces P, P1, P2, P3, P4, all I have to do is cumulatively add all these and see their effect on V. So therefore if I have a section of the beam, all I have to do is look at all the vertical forces, keep on adding their effects. If there is a downward force, that will produce a shear equal to minus P. If there is an upward force, it will produce a shear equal to plus P. So as you said, suppose if there is a force AY acting at A, what will be its effect on V? It will produce a force equal to plus AY. So that means the net shear force at V will be plus AY minus P. So instead of doing all the calculations, I will directly write this. I keep on adding all the forces algebraically, and that gives me the shear force. Is that clear? So this is if there are discrete forces. Now what, as we had in a section, there was a distributed force. So what I will do is, for that distributed force, wherever I have cut it, I will find its equivalent and I will add that. Whatever is the equivalent, that means the area under that loading, that is the equivalent force. I will just add that, and plus or minus will depend on this. So if there is a downward force, so what I can do is I can modify this. I will put it, if the force is upward, then it will be, an upward force will produce a shear force equal to plus P. So therefore these things I had this seems to have this thing, but otherwise this was in red and this was also. So, the parts in parenthesis go together, the parts without parenthesis they go together. So, that is how this has to be read. So, a downward force induces on all sections V is equal to minus P, and upward force induces on all sections V is equal to plus P. So, either you read it without parenthesis or with parenthesis. Okay. So, this is one thing. Now, the second thing we would like to do is what happens to the moment. I have a downward force P. So, now the moment here, this is how the bending moment is specified by a counterclockwise force. So, now what I have is a downward force P. What is the moment because of P? P times zeta. And what does it do? So, it will be a downward force of P will induce on all sections to its right a moment m is equal to minus P times zeta, where zeta is the distance between the cut section and the point of application of P. Let me first write this and then I will explain this again. Downward force P, which is basically a minus force, this induces on all sections to its right bending moment m is equal to minus P zeta, where zeta is the distance from the cut section to the point of application of P. And now, is that clear? Because that is the effect of P on the bending moment. So, now what you will do is, if suppose there are 3 or 4 forces on the left, how will you calculate the bending moment on the right? You add the contribution of each of these single forces, P1 zeta 1 plus P2 zeta 2 plus P3 zeta 3 plus P4 zeta 4, and with the appropriate signs. So, you add them up, you will get the cumulative bending moment at m. Okay. Now, if this is a distributed force, if any of these is a distributed force, then what you have to do is you have to replace it by a proper equivalent. What is the equivalent of the distributed force and where it acts? And then, but keep in mind, the mistake we tend to make is zeta is the distance from this point to P, not from origin to P. Normally, we are used to taking moments from the origin. Here we are talking of this distance zeta, which is basically from the cut section to P. Okay. So, that is the second thing. Now, we have a third thing. In addition to the force, I may have there may be a counterclockwise moment m1, which is somewhere on the beam, as we showed, as in an example which I showed here. In this case, there is a moment m1 which is acting at a point. Now, what does m1 do on sections to its right? So, here we have a counterclockwise moment m1, this is m, So, what is the role here, and this gives us the third point, that let me write this, a counterclockwise couple M1 induces on all sections to its right a bending moment M is equal to minus M1. So, a counterclockwise moment on, so once you encounter a counterclockwise moment on all sections to its right, when you write the bending moment, you have to add a moment equal to minus M1. Okay. Now, what will this moment do to the force? Will it create any effect on the shear force? It will not create any direct effect on the shear force. Why do I use the word direct? It will affect the reactions. So, because of the reactions, eventually the shear forces may change, but directly the moment will do, a point moment will not do anything to the shear force. So, using these three rules, we can then draw some simple bending moment and shear force diagrams. So, what let me do is I will take a very simple example to end the class today, so which I should be able to finish. So, let us take a very simple example today just to work out this. Let us see, I have a beam AB, this is 2 meters, I draw a simple beam A, B, C, D. Beam A, B, C, D shown above. And we have to draw we use these notations SFD for shear force diagram, BMD for bending moment diagram. Okay. So, now the first thing we have to do is find the reactions at B and D. So, we draw the free body diagram. So, first thing we solve for the beam, we have By, Bx, we have Dy, we have 40 kilonewtons and we have 20 kilonewtons. So, sigma Fy is equal to 0, sum of moments about D is equal to 0, you can do these, and what you will get is By is equal to 50 kilonewtons and Dy is equal to 10 kilonewtons. You carry out the moment analysis. So, take Bx is obviously 0 and you take moments about one of these points. So, sum of these is equal to 60, one of them is 50, the other is 10. This comes from moment balance. Okay. So, this you will get, I think there is no big deal. So, now let us draw the full loading on the beam. It starts at 0, we have 2, 4, 6. We have a load of 20 kilonewtons here. At point 2, we have 50 kilonewtons. At point 4, we have 40 kilonewtons, and at point 6, we have 10 kilonewtons. So, this is the what I can call as the loading diagram of the beam. It includes the external reactions also. So, these are the forces acting on the beam. Okay. So, now when I want to write the expression for the shear forces and bending moment. So, we start from 0 and the first eventful thing which is happening is at 2. From 0 to 2 there is no change in the loading. So, therefore, from when x is between 0 and 2, what is the shear force? We have a force 20. So, that means if I am basically in my mind I make a cut section from between 0 and 0.2 is somewhere here. I just have a single force 20 which is minus. So, therefore, going by my rules, my rule says a downward force V induces a downward force of P induces shear force V is equal to minus P. So, directly without doing anything I write my shear force is equal to minus 20. Okay. Now, what about the moment? Now, the section x which I cut, this is at this, and what we have is a downward force V in P induces on all section a moment equal to minus P zeta. So, therefore, moment will be equal to if I am looking at this cut section, there is only one force which is equal to 20. So, therefore, the moment here will be this distance is x. So, moment is equal to minus 20x, this is kilonewton meters and this is kilonewtons. I should always put the units. Is that clear? So, if I start drawing a diagram, I will start from 0 up to 2, then the shear force V will be minus 20. And if I draw on the same axis, I put the bending moment, it is minus 20x, that means it starts from 0, it goes up to minus 40. So, the bending moment diagram starts from 0, shear force is minus 20 all the way up to 2, and bending moment starts from 0, it is a straight line up till minus 40. Is that clear? So, this is the shear force and bending moment between 0 and 2. Next, let us move for x between 2 and 4. That means, now I am talking of x here between 2 and 4. What will be the shear force? So, shear force, what I will do is I have 20 and 50. So, minus 20, the contribution of this on any section will be minus 20, and now I have another force equal to 50. So, this also contributes. So, I have minus 20 plus 50. So, that means from 2 to 4 the shear force will be equal to minus 20 plus 50. So, this will be plus 30 kilonewtons. That means, at this point 2 I will go in, there is a plus 30, then shear force will become plus 30 from this point onwards. Okay? घर का भेदी लंका ढाए. I think that is what is happening here. Please pass the sheets on and they can be. Now, what do I do to the moment? Now, moment, let us look at this. Now, what is the contribution to the moment from 20? Now, this distance, this section is at x. So, it will be still minus 20x. Now, what is the contribution from this 50? 50 is a plus force. So, now the contribution will be P zeta. So, it will be plus 50 multiplied by zeta. What is zeta? The total distance is x, and the distance between this cut and the point where 50 is acting is how much? x minus 2. So, that means the bending moment there will be minus 20x plus 50 multiplied by x minus 2. So, I keep on adding like this. So, therefore, the bending moment here will be minus 20x plus 50 multiplied by x minus 2. So, now what I can do is, I realize this is a straight line. So, I calculate the value of m at 4. At 4 this will become 50 times 4 minus 2. So, that is 50 times 200 minus 20 times 4 80. So, that means plus 20. So, what will happen in the bending moment? It will go from minus 40 to plus 20. So, the bending moment diagram. So, let us look at this. Let us draw these two diagrams again. So, shear force will start from minus 20, at 2 it will jump to plus 30, and this is the distance 4. What happens at 4? We will see. At 2 there is no unique value, there is a jump, there is a step, there is a discontinuity in the shear force. At 2 minus, the shear force is minus 20, at 2 plus, the shear force is plus 30. So, it is a discontinuity, it is a step function, okay? It is a discontinuous function. Now, the bending moment, as we saw, it started from minus 20, it started from 0, and this was minus 40, and the value we saw is at x is equal to 4, this is plus 20. So, what I am going to do is, from this point till plus 20, I know this is a straight line. So, the bending moment takes, it goes from minus 40 to plus 20. Okay. Now, similarly, the last thing we can do from 4 to 6. From 4 to 6 what happens? There is a force of minus 40. So, what will it do to the shear force? Shear force will go down by 40. So, that means when I look at from 4 to 6, the shear force will be equal to minus 20 plus 50, and then I have this value of V, which is equal to, how much is it? It is minus 40. So, this will be equal to minus 10. So, that means the shear force at this point in the diagram, this will go down to minus 10, it will continue till 6, and at 6 we see there is a force of plus 10, this should match out, it will go to 0. Now, what about the bending moment? So, first I copy these two things, minus 20x plus 50 times x minus 2. These two contributions were already there. Now, what I do is, I look at this contribution, this is my new x between 4 and 6. So, now the new contribution has to be added is minus 40 times this distance from x1 to 4. So, it is x minus 4. So, minus 40 times x minus 4 has to be added to the bending moment. So, therefore, I will go from here, and in the bending moment I will put minus 40 times x minus 4, and if you put x is equal to 6 here, you will get the answer as 0. So, that means this bending moment at point 6 reaches a value 0. So, therefore, this graph will be like this, it reaches a value of 0. So, this is how we complete the shear force and bending moment diagram for a simple case like this. Is that fine? In the next class, I will do two more things. I will look at a distributed function, and I will derive a differential form of equation for shear force and bending moment, and then I will take an example where we will take a distributed function, because this is a very simple example. I will take an example where we will have either a triangular loading or a uniform loading, cut a section, how does it affect when you cut a section there. So, that is what we will see in the next class. Okay? Thank you.